Today I'll talk about aromaticity and Huckel's rule. So what is aromaticity? Aromaticity is defined as the stabilizing energy imparted in the molecule or ion that obey the four rules. So what are the four rules? Let's take a look at them. The first rule indicates that each atom should have a p orbital to allow for contiguous overlap so that the electrons can be delocalized. The second rule is the molecule or the ion should be cyclic. It's okay to have more than one ring. The third rule is the structure of the molecule or ion should be planar. And the last and most important rule is the Huckel's rule. What that means is the molecule or ion should have 4n plus 2 electrons that are delocalized, where n is 0, 1, 2, 3, and so on. Let's take a look at examples of aromatic molecules and ions. Recall that they need to obey all the four rules. Let's start with a simple example. This cyclic cation is derived from cyclopropene. It has one double bond. That means it has 2 electrons for delocalization. It's a cyclic molecule. The carbocation carbon has an empty p orbital that allows for contiguous overlap, and hence this cation obeys all the four rules, and hence it's aromatic. Let's look at the second example. It's a heterocycle. It has a nitrogen atom and a sulfur atom in the ring. One of the lone pairs on the sulfur atom, which are red in color, are in the p orbital and are available for delocalization. So in all, there are 6 electrons available for delocalization. The molecule is cyclic and planar, and it obeys the Huckel's rule of 4n plus 2. In this case, n is equal to 1. That's equal to 6 electrons that are delocalized, and hence this compound is aromatic. Let's look at another example. In this case, there are 5 double bonds. That's equal to 10 pi electrons that are available for delocalization. The molecule is cyclic, and it obeys the Huckel's rule of 4n plus 2, where n is equal to 2 in this case, and hence this molecule is aromatic. Note that the lone pair of electrons on nitrogen do not take part in delocalization. They are in the sp2 hybrid orbital. This is a big polycyclic molecule. It has 7 double bonds. It does obey the Huckel's rule of 4n plus 2. In this case, n is equal to 3. It is planar, and it obeys all the four rules, and hence this molecule is aromatic. It's called 14-anion. Let's look at additional examples of aromatic compounds which have 6 delocalized electrons. Benzene is a famous example. It is planar in structure. It is cyclic. The double bonds are in conjugation. There are 6 electrons available for delocalization, and hence it obeys all the 4 rules, and hence it is aromatic. Next example is an anion. This is a cyclopentadiene anion. The lone pair of electrons on the carbon atom are in the p orbital, and hence they are available for delocalization with the electrons of the 2 double bonds. The entire molecule, anion, is cyclic. It obeys all the 4 rules, and hence this anion is aromatic. This compound is called furan. It has 2 double bonds in a ring, and one of the lone pair of electrons on oxygen are in the p orbital, and hence it does obey the Huckel's rule of 4n plus 2, since there are 6 delocalized electrons. It's aromatic since it obeys all the 4 rules. This molecule is pyridine. In pyridine, there are 3 double bonds. That means there are 6 delocalized electrons. Each double bond is equal to 2 delocalized electrons. Note that the lone pair on nitrogen is an sp2 hybrid orbital and does not take part in delocalization. Next example is a heterocycle molecule. In this case, the lone pair of electrons on nitrogen is in the p orbital, and hence it's available for delocalization with the electrons of the double bond. The molecule is cyclic and it obeys all the 4 rules, and hence pyrrole is aromatic. Let's go on to the last example. This last example is a cation. It's a 7-membered ring, and it has 3 double bonds. That means it has 6 electrons for delocalization. And if you recall, a carbon atom which has a positive charge has an empty p orbital, and that empty p orbital is available for delocalization with the pi electrons of the double bond. Hence, it obeys all the 4 rules, and the cation is aromatic. Now that we have covered several different examples of aromatic compounds and ions, we'll move on to antiaromatic compounds. So, what are antiaromatic compounds? Any molecule that has 4n number of electrons that are delocalized and that obey only 2 or 3 of the rules are antiaromatic. Let's look at this example. You can see that there are 4 double bonds. That means it has 8 electrons. It obeys the 4n electron rule. The 4 electrons are delocalized, but they are not in a ring, and hence it does not obey all the rules, and hence the compound is anti-aromatic. Next example, this molecule is a bicyclic compound. It's planar, it's cyclic, and the double bonds are in conjugation. However, it has 4n electrons. That's 8 electrons. N is equal to 2 in this case, and hence it's anti-aromatic. In this particular example, this molecule is not planar, and hence it is anti-aromatic. It also has 8 electrons. The last example is that of butadiene. So butadiene is conjugated. It's cyclic, it's planar, and it has 4 electrons that are delocalized, and hence it's anti-aromatic. Let's move on to understand what non-aromatic compounds are. So any compounds that do not fit into the aromatic or anti-aromatic category are called non-aromatic compounds. Let's look at this example. It's an open chain molecule. It's hexatriene. It's not cyclic, and hence it's non-aromatic. Another example of a non-aromatic compound is this molecule right here. It's cyclopentadiene. Observe that the conjugation or the overlap is broken due to the presence of sp3 carbon atom right here, and hence it's not conjugated, and so it's non-aromatic. The similar situation arises in the next example, where again this carbon atom is sp3 hybridized, and so the conjugation is broken. And so both these compounds are non-aromatic. Thank you for watching. Please like and subscribe for more.